Hello again everyone, welcome back to ptet.chemistry channel. In this tutorial video, I'll continue this section B, kind of topical MCQs on section 10.2. That is on hydrocarbon chemistry, that is alkane and alkenes, alright? So you can use this tutorial video to revise for your theory paper as well, because MCQs assesses more than just one particular learning objective, as you will have realized if you have done one of these MCQs before, alright? So in this question, you have this sex attractant of this housefly with this following formula. So it's got 7 CH2 there, and it's got 12 CH2 there. If I were you, I could probably be thinking about, do I want to draw out the skeletal formula? Actually, I can draw out the skeletal formula, because what I can do is I can simplify that as R1, and I can simplify that as R2, because that is basically a straight chain alkane. It's not branch. That CH3 CH2 7, that means it's a C8 it's a C8 straight chain. This is a C12 plus 1. This is a C13 straight chain. What I could do is, then it becomes very clear. You could have R1H, you could have R2H, which, guess what? Which means you could have cis and trans as well, because the R2 could be there, or the R1 could be here. Well, I mean, you could have cis and trans like that. So that would be your trans, that would be your cis. But they are not asking on cis or trans, because they simply give you the structural formula. And as you know, you can't tell geometric isomers apart, because they are stereoisomers, because stereoisomers have the same molecular formula and the same structural formula, but different arrangement of atoms or the groups in space. Alright, so really, I mean, it's a test of your definition of stereoisomerism, something they like to ask in a theory paper, of course. Alright, not that they ask you here. What do they ask you here? They ask you on oxidation, call alkaline KMnO4 to give you diol, and that is precisely correct, because that is the chemistry of alkene. You can get diol, meaning the OH and the OH like that. I put it in an inverted comma. I'm not comfortable writing just drawing this out, because the carbon hasn't formed 4 bond, and I don't want to be drawing this out again, but you should be able to think about this chemistry. This is a coal. It works in alkaline condition. It also works in acidic condition. Yeah. So coal equals acidic, or coal equals alkaline, KMnO4. This is what you call a mild oxidation. It is still oxidation, because each of the carbon in the carbon-carbon double bond has gained an oxygen. In organic chemistry, gaining oxygen or losing oxygen, gaining hydrogen or losing hydrogen, those are more important rather than using electrons, rather than using oxidation number, because we are dealing with organic compounds. All right, so those are more relevant in the context of redox changes for organic chemistry. We also know that first statement is correct, because it can do addition reaction. It can do electrophilic addition across the carbon-carbon double bond. All right, and then they're saying that this thing is also optically active. This is a straight chain carbon. Okay, there are carbon with 3 hydrogen, there are carbon with 2 hydrogen. This is a carbon with 2 hydrogen throughout the straight chain. This is a carbon with 3 hydrogen. You don't get any chiral center on this carbon or on this carbon, meaning no chiral center on R1 and R2. Whether you're cis or trans, there's a different story. But optical isomers are different from geometric isomers. Okay, so even though your geometric isomers doesn't mean you have optical isomers. This is to do with chiral carbon. Okay, so no chiral carbon here. You have no carbon bonded to 4 different groups or atoms or substituents. So that means 3 is incorrect. Therefore, your only correct option is 1 and 2. So next up, which compounds can be obtained from ethene in a single? So you need it in a single reaction. So number 2 is a polymer. So of course you can get it from ethene. If I just draw the monomer, which you will have done this in GCSE or O level, you have n number of ethene, which is your monomer, and then you will get addition across the carbon-carbon double bond. So what you will get is you will get this polymer where you have lost the carbon-carbon double bond because you did something called addition. And because you're forming polymer, this is called addition, polymerization, something you have done in GCSE and also O-level. So what happened there is we can do this all in one go, and yeah, so that's polymerization in one step. Next one, this is an alkane. It's a ethane molecule. It's a 2-carbon alkane, which of course you can get it. So I'm just writing the structural formula. You can get it by reduction. So this is called reduction. People like to call it hydrogenation, but you forget that it's also actually the type of reaction is not hydrogenation. Hydrogenation is the name. Name of reaction is hydrogenation. The type of reaction is covered under introductory organic chemistry. In your specification is called reduction. All right, where each of the carbon have gained hydrogen. This carbon has gained hydrogen. This carbon has gained hydrogen. Gain of hydrogen is reduction. All right, which of course, as this has been reduced, this has been oxidized. Okay, so one is also correct. You can do in one step, which of course you also need nickel catalyst, and you need high temperature. So roughly around 200 or 300 degrees Celsius will be all right. Next one is a diol. Number 3 is a diol. It's a ethane 1,2 diol. And we just covered in the previous question that you can get from an alkene to a diol. You can do oxidation, all right? And you can get diol, all right? So CH2 and then there's OH. That is your ethane 1,2 diol, because you have an OH at the 2 position, 1 and 2. So you can use acidified KMnO4, but it needs to be cold, dilute. Okay, these are the conditions that you need for this reaction, and it is called an oxidation as the type of reaction. All right, so it's actually a mild oxidation of alkene, because when you use hot and concentrated, you can break this totally, and because this is a CH2 terminal, it will just give you CO2. Same deal here. If this leads to oxidative cleavage or the oxidative rupture of the carbon-carbon double bond, when you use hot acidified KMnO4, you're just going to get CO2 from both sides. All right, anyway, you can get all 3 in one step from alkene, from ethene specifically. So there's A for you. For this next question, you have deuterium. So deuterium is the hydrogen 2, meaning to say that is the nucleon number of the hydrogen. So what we have is DBr has the same chemical property as HBr, because same number of electrons. Chemical property is to do with number of electrons. You only have a difference in the number of neutrons. Neutrons are uncharged. Neutrons are in the nucleus. You don't do chemical changes with the neutrons or with the nucleus. That is to do with physics and radioactivity. Something to do with the nucleus involve radioactivity. We deal with chemistry, chemical properties. We deal with outer shell electrons. All right. So which one can you make from DBr with another compound in a single reaction? Okay, so just looking at option 2 first. So option 2, you have Br, CH, and then you also have Br, but what you have is D. So what can we make? Could be made by reacting DBr with another compound. So I guess the key here is another compound. Well, you could get this from having, I don't know, if you have the cis or if you have the trans, you could react that with DBr and it would lead to that. This is your classic electrophilic addition. So this is one of the key mechanisms that you have to know for A-level chemistry, not just in AS. So you can watch my topical playlist where I talk about how to think through the mechanism specifically, all right, so that you'll never ever forget it. If I have the first one, I guess you can imagine having the double bond there originally, but I don't want to draw the full double bond there because this is a alkane is a cyclohexane. So if I have these, nope, I don't have the DBr initially, so I can do another electrophilic addition. This is with DBr. This will also be delta plus, delta minus, and of course, you can do the mechanism, and then you get the carbocation intermediate, for example, like this, and then you have the Br, the lone pair of the Br attacks the carbon with a positive charge, and then you can get DBr. So this is not in 2 steps. This is an intermediate, by the way. This is an intermediate, meaning to say when you have your energy profile diagram, extent or progress of reaction, you are going to get, I'm assuming it's exothermic, okay? I'm assuming means I don't know for sure, but I'm assuming that it is exothermic, and that is a wrong reaction profile diagram because it proceeds via intermediate. So what it will do is it will go that way, and then the second step is faster. All right, the second step is faster because negative charge, positive charge, they like to attract, so the activation energy for the second step is lower than the first step. All right, and that is your intermediate. This is your reactant, these are your product. All right, anyway, my point is you can get one in a direct electrophilic addition reaction. All right, how about number 3? Number 3, if you can't think about D, think of it as being OH, then what can we have? This is DBr. They are on the same carbon. You see, they are on the same carbon. So here the OD and the Br is on the same carbon. That is a problem because whenever you do electrophilic addition, you add across the carbon. You see, you add across the carbon such that one of the D end up here or here, one of the Br end up on the other side. Here, one of the D end up here, the Br will end up here. If the D is here, then the Br will end up there. So here is on the same carbon. You can never get this from the direct reaction of DBr with something else. You cannot get this from a direct electrophilic addition reaction of DBr with another compound. So there's 1 and 2 only. So there's option B. In this next question, so we have these 3 hydrocarbons and we have this hot acidified KMnO form. So we're going to do an oxidative cleavage or oxidative rupture. Maybe I just stick with cleavage, alright? Cleavage of carbon-carbon double bond because this is an extreme condition. So we want to get 2 organic compounds. We want both of them have a ketone group, okay? Both of them have a ketone group. And you know that when you have RCH carbon double bond, that will give you RCO2H, which is a carboxylic acid. When you have RCr, so your carbon of the double bond, it's bonded to 2 other carbon, whereas your carbon of the double bond is bonded to 1 other carbon and 1 hydrogen. So here you will get a ketone, all right? So what are we looking for? We are looking for a carbon of the double bond bonded to 2 other carbon, all right? So I can tell you, you get 2 organic compounds. So there are 2 conditions here, right? 1 and also 2, all right? So if I split my alkene, if I check number 2 first, all right? If I split my alkene, there's only 1 alkene, I would just get 1 product. I would not get 2 organic compounds because when this break, what you will get is this side will still be bonded to this side. When you want 2 organic product, you need 2. You need 2 of it because you are in a cyclic thing. If I show you what I mean, okay, ideally in a real exam situation, you might not have to draw it out. It's just about the logic. This will only give you 1 organic compound. I can tell you 2 already is wrong, all right? And I also can tell you a second reason why it's wrong. Because if you look at here, this is a this is a carbon, there's a hydrogen, and there's a carbon. So it's a RCH double bond. You get carboxylic acid here, and you get a ketone here. You want 2 organic compound, which this one already doesn't give you. You want both contain a ketone group. This will give you a ketone because it's a carbon carbon bonded to 2 other carbon to give you a ketone there, but not this one. This one will be a carboxylic acid. You want both to contain a ketone, so this one is already incorrect as well. So both the first and the second condition are already not satisfied by 2. You only have one answer, which is D. In a structure paper, however, they will ask you draw all the possible product. So when you cleave that, you will get ketone. Follow it through, you will get a carboxylic acid because there's a RCH, there's a hydrogen, so we follow that. Carboxylic acid. R dash, doesn't matter, carbon of the double bond bonded to 2 other carbon. Okay, ketone. So there's only one product, and you can tell that doesn't give you 2 organic compounds. Alright, how about if I draw number 1? If I draw number 1, I get that, and that, and that. I use a different color. I break that, and follow that. And then this is a RCH, this is also a RCH, but this is a carbon bonded to 2 other carbon, okay? So there's carboxylic acid, but there's my ketone, and that is my carboxylic acid, okay? Are they the same or are they different? 1, 2, 3, 4. 1, 2, 3, 4, 5. The number of longest carbon already are different, so there are 2 different products here. And then each has a ketone. Oops. You have the ketone there, and you have the ketone there, alright? And then you can, of course, practice drawing out the other one, and you will see that you don't get a ketone because this is a RCH double bond, this is a RCH double bond. This will give you a... In fact, when you cleave this bit is very, very, very interesting because what you will get is this. Alright, and this is called ethane dioic acid. Alright, and you actually do not get this. You do not get this. This is what you first obtain. But what you get is you get CO2 and H2O because you get oxidation of ethane dioic acid. So have a look through your syllabus and you will see that in the presence of extreme conditions, this would not survive. You would not be able to get this because this will be further oxidized by this all the way to CO2 and H2O. It's together with methanoic acid. Methanoic acid is another one that can be oxidized by this. Even though they are carboxylic acid, they are both oxidized to this and this. Alright? But of course that will give you ketone. That will give you ketone, but you will just get one organic compound because this get further oxidized. Alright? Okay, this is the last question of this 5-question series on topical MCQs of hydrocarbons. What type of reactions are undergone by 2-bromopropane? So 3 carbon, 1, 2, 3. You have a bromine there. This is a secondary halogenoalkane. You will learn more of this under halogenoalkane topical playlist. I forgot whether it's 10.4 or 10.5, yeah? But the carbon bonded to the halogen is bonded to 2 other carbon, and there's a hydrogen there, alright? The carbon bonded to the bromine or the halogen is bonded to 2 other carbon, secondary halogenoalkane. Undergone, right? Well, it has alkane. It has a CH alkane. So the CH can undergo free radical substitution. Can you do elimination? So usually in skeletal formula, we don't draw the hydrogen bonded to carbon. I'm just showing it here because I want to show you that you can eliminate. So when you do ethanolic, so you'll learn more of this in halogenoalkane chemistry as well. Ethanolic NaOH and reflux, then you will get that plus HBr. So that is your elimination. One substance give you 2 other things. That's elimination. Can you get nucleophilic substitution? Of course, when you have aqueous NaOH and then you reflux it. So aqueous mean in water, ethanolic mean in ethanol, not in water. Different condition, yeah? So the name of this reaction is called hydrolysis, but the type is still nucleophilic substitution, or rather the mechanism. Okay, so all three are entirely possible. So the answer is A there. Alright, so we reached the end of this 5-question series on this section B kind of topical MCQs. Make sure you subscribe to the channel, click that button on the bottom right, share the channel with your friends, your class chat group, your juniors in school, your seniors in school, if you are a lower 6 student, and yeah, and see if it benefits them the way it benefits you, and check out the other topical MCQ playlist. Alright, thank you for sharing, and thank you for watching. See you in the next video.